Hi everyone, my name is Xu Chen. I'm a PhD student at the University of Electronic Science and Technology of China. The paper I will presenting today is titled Leon, a new framework for query optimization. This work is from UESTC and Huawei. In this work, we use machine learning method to aid the traditional query optimizer. In the following slide, I will introduce our work from the perspective of why, how, and what. First of all, why machine learning is utilized for the query optimization. First, it is widely acknowledged in the previous research that the traditional query optimizer performance is not satisfactory. This is due to the fact that the traditional query optimizer relies on the heuristics. And second, the query optimizer is hard to develop and maintain. It needs human experts to tune for certain use cases, such as the data distribution and the hardwares. And also, it takes thousands of person engineering hours, especially on the cloud. However, machine learning method can leverage many valuable execution feedbacks from the database to enhance its performance. Next, what machine learning can do and cannot do for the query optimization. First of all, machine learning can learn domain-specific knowledge, such as the data distribution and workload patterns. It can self-adjust to the given data and workload, and also beyond the human expert capability. However, machine learning cannot replace the basic knowledge in the database systems. There are two reasons. First, the traditional query optimizer has many basic knowledge, such as the transformation rules. And secondly, the traditional query optimizer is general purpose. On the other hand, the machine learning models suffer from the cold start problem. It takes a long time of training before it can become practical and usable. We believe that machine learning models can compensate for the domain-specific knowledge required by the traditional query optimizers. In other words, machine learning needs to aid the traditional query optimizer. Let's first look at some prior works in the machine learning for query optimization. We divide them into two big categories. First is the ML replaced, and the second is the ML aided method. The ML replaced method refers to the reinforcement learning method to build a standalone query optimizer that generates the query plans. We find that the fundamental knowledge in the traditional query optimizer cannot be learned by such learning models. They show some promising results. However, they still suffer from the practical barriers, such as the long training time and the long tail latency. On the other hand, the ML-aided approaches build the machine learning models on the top of the traditional query optimizers to enhance the optimizer performance. We also categorize them into two categories. First is the black box method, and the second is the white box method. For the black box method, they only use the coarse-grained optimization choices, such as enabling or disabling some knobs for the entire plan space. However, the global choice calls suboptimal plans. For example, a subplan is optimal with the next loop join, but it can be discarded because a next loop join has a poor performance on the other subplans. For the black box method, they aim to learn a parameterized model to steer the expert cost model or the cardinality estimator. The major difficulty we find is that the plan space is so large that it's hard to learn it accurately. Therefore, we need to use and train machine learning models properly. Leon choose the ML-aided and white box path to aid the traditional query optimizer. Next, how can we use machine learning models to aid the query optimizer? First, we described a high-level overview of the traditional search engine. In general, it has 4 steps. The first is plan enumeration. The optimizer will enumerate the logical equivalent plans by applying the transformation rules and then apply the physical implementations to the logical plans. The equivalent set is defined as the set of plans that are logically equivalent and have the same physical properties. Actually, there are no heuristics involved in this step, and it leverages a lot of basic knowledge in the optimizer. The next step is the cost computation. The cost computation means the optimizer collects the statistics for every plan and compute the cost by a cost model. The next step is the cost comparison and memorization. The optimal plan and the corresponding cost from the equivalent set is chosen and memorized in a lookup table. Finally, we go back to the step 1 and search in the next equivalent set. In Lean, we enhance the traditional query optimizers in the 2 steps. The first is the cost computation. We use machine learning mixed cost model to enhance the traditional cost model. If the machine learning model makes bad decisions, it can easily fall back to the traditional query optimizer. And the second is the state pruning. We use machine learning models to prune the redundant search space so that it decreases the extra overhead. First, let me introduce the mixed cost model. Our key insight is that we regard the query optimization as a ranking problem and trained the machine learning models in a learning to rank paradigm. Specifically, we learn a score function that mapped a plan to a scalar value, or called score, to rank the plan from the same equivalent set. Note that the previous works used machine learning models to predict the latency of plans in the whole plan space. In practice, such learning objectives have significant prediction errors. So Lean focuses on the ranking of the plans in an equivalent set instead of the actual latency value, which improves the prediction accuracy. Furthermore, we formalize the ranking problem into a pairwise ranking problem. Given a pair of physical plans, plan 1 and plan 2, which is derived from the same equivalent set. We use machine learning models to predict which plan has the higher ordering or higher score. Learning to rank paradigm has been studied extensively in the recommendation system. It has been shown that forecasting the relative order is more closely related to the nature of the ranking than predicting the absolute value. So pairwise techniques performs better in practice than the point-wise approaches. And another key challenge is to explore extra experience instead of relying on the current best plans. Here, the exploration means we need to occasionally execute unfamiliar plans to find better plans. In this work, we measure the uncertainty inherent from the machine learning models. The key observation is that the error classification shows larger uncertainty as shown in the line plot. So, we designed the machine learning model to quantify the uncertainty to the plan ranking. Specifically, for better exploration, we have 2 stages. The first is the top K exploration. For an equivalent set, we first find the top K ranking plans based on our ranking model. And then, we measure the uncertainty of the top K ranking prediction. We pick plans with the highest uncertainty among them and collect the corresponding execution feedback in our experience pool to train machine learning models. Lastly, we use the plan pruning strategy to remove the extra overhead. Query optimization efficiency is an important criteria that we believe. So, to improve the plan search process, we use machine learning guided pruning strategy during search for the optimal plans. The key insight is that there are many inferior subplans during the plan search cannot be extended to the complete plans. So, machine learning models can learn to prune the redundant search space based on the overall ranking for the complete plan. With the machine learning model guidance, we find that search space can be pruned safely without hurting too much performance. So, How does Leon performance? We compare Leon to the traditional database, Postgres, and there are several learning-based methods relevant to Leon. BELSA is the SOTA machine learning-based replaced method that learns an end-to-end query optimizer based on the reinforcement learning. BAL is a SOTA black box method that tunes the knob of the traditional query optimizer. We use 4 public benchmarks in our experiment. First, we show the overall latency. In this table, it shows the workload runtime of different methods on different datasets. From this table, we can show that the Leon generates superior execution plans that run up to 1.9x faster than the traditional query optimizer, and 1.4 faster than the learning-based query optimizer. Next, we show the query regression analysis. In this figure, we show that every query performance compared to the Postgres. The x-axis is the query execution runtime from PG. It shows how heavy a query is. Y-axis is the runtime from different learning-based methods compared to PG. The lower the runtime means the better performance. Overall, Leon shows up to 1.6x performance regression, while other learning-based methods show 9.6 regression. It's worth mentioning that Leon exhibits a significant reduction in the query performance regression while maintaining similar performance on queries that are inherently fast to execute. Next, we show the training efficiency. That is the change of the test query performance with the training time. The performance of Leon remains robust compared to the other learning-based methods during the training process. Leon shows consistent performance with the traditional database even at the start point. Leon takes only less than 3 hours to surpass the expert optimizer, which is much faster than the other learning-based query optimizers. Finally, we demonstrate how Leon adapts to the dynamic workload during the course of training. To show the change of the workload, in every 2 hours, we dynamically introduce 2 new templates to the current training and testing queries while keeping the previous query. Overall, Leon consistently outperforms PostgreSQL and BAL at every stage, with less initial performance regression. That's all for my presentation. Thanks for listening.